Good morning together. My name is Benedikt Kölsch, and I'm going to give a presentation today about some work where we compared airflow and acoustic measurements for the evaluation of building leakage paths in a laboratory test method. Here I would like to discuss a new method for the single air leakage evaluation. And I will start with a short introduction here. As we all know, air tightness is important for all of us, and uncontrolled airflow, like already discussed by the previous speakers here, and seen in the picture on the right, may lead to an increase of consumption heating and cooling energy. The most prominent method for measuring the air leakage is the well-known blow-order test, which has mainly three purposes. The first one is actually measuring the leakage of buildings or buildings parts. The second one is comparing the relative air tightness of different buildings among each other. And the third one is determining the reduction of air permeability, for example, after the implementation of improvements. But leak detection is very time consuming and heavily depends on the inspector who's doing the measurements, and quantification of single leaks is very cumbersome in buildings. So we are going to investigate supplementary methods for the leak quantification, but we will still have these blow-order tests as a basis for the subsequent analysis and as a comparison in this presentation. So we are going to investigate acoustics. We assume that acoustics, the sound may take predominantly the same paths as air does in the blow-order test. And moreover, it can have the advantage that it can be used while the building is in use. It is, in contrast to the blow-order test, independent of pressure differences, and in contrast, for example, to methods like the infrared thermography, independent of temperature differences. Further, microphone arrays, for example, as seen here on the right side, may have the potential to localize leakage spots. But size quantification is still very difficult, so I'd like to answer the question if it might be possible to quantify single leaks with acoustic methods. For this reason, we built a laboratory wooden test box, like seen here on the right side, with the goal to simulate realistic leakage scenarios on a model scale and to be able to compare them in a controlled environment. So within this box, we did we investigated different wall configurations and separated this box into two chambers. Here we were able to simulate different scenarios, and I will talk about this later here in my presentation. First, we were able to do some airflow measurements where we installed a blower on one side of the laboratory test, blowing air through these deliberate openings in the separating section in between the two chambers, and simultaneously measuring the pressure difference across the chamber, like it is done in blower measurements. Within the same setup, we did acoustic measurements where we put microphones in each of these chambers and a speaker in one of the chambers, and measured the sound transmission through the walls. All in all, we investigated 43 different wall configurations and were able to compare them among each other. For all these configurations, we put a wooden plate between both of these chambers with a slit in the upper part of the plate. And for all configurations, this slit has had a fixed length of 180 millimeters. But first, we investigated different slit heights here. The largest one was 5 millimeters, and the lowest one was 0.25 millimeters high. Further, we changed the number of walls, so we investigated only single walls between them and double walls with an air gap in between. Then we changed the distance between these wall constructions with a parallel leak between 100 and 150 millimeters. And to make it more realistic for some measurements, we put insulation material inside as well. as it is done in real buildings. And we connected the slits, for example, with a channel if they are parallel to each other. Due to the fact that in real buildings, often the leak is not straight through the wall, as it is done here, we investigated non-parallel leakage paths in this model scale as well, where we connected them and with and without any connection. For reference purposes, we investigated blank walls without any openings as well. Here are some pictures how it looked like in our setup. This is, for example, a setup with insulation material in between. This is a straight connection between both walls, but without any insulation. And this is, for example, a non-parallel leakage path with a connection between both of them. So as I told you earlier, first we did some airflow measurements. They looked like this. So we had a blower on this bottom part of the box. This box was connected to the box. This blower was connected to the box with a Venturi airflow meter. We just measured the pressure difference across this meter, which is proportional to the airflow through the meter. The box was sealed on top for the pressurized chamber and open to ambient condition in the second chamber. So we only needed to measure the pressure difference in the static pressure in one of the chambers, in the pressurized chamber. And we did it with a copper tube flushed on the inner side of the wall. And therefore, the pressure difference between these two chambers can easily be calculated between ambient conditions and the pressure in one of the chambers. I will now show you some example results of these 43 different configurations. Here, for example, is a configuration where we measured a double wall construction with 100 millimeter distance without any insulation material and a straight channel connecting these leaks. And here we only changed the slit heights between the measurements. On the x-axis, you see the pressure difference, and on the y-axis, the airflow rate, as it is done for the blower door tests. All the dots are measurements for these different pressure difference airflow rate combinations. And the line is a fitted blower door function between them. As we might expect, we see that for the larger slit, the large slit is much higher, has a much higher airflow than all the other slits. But even though the two smallest slits, which are very close to each other, we can still see a small difference between them. For a subsequent analysis and comparison with the acoustic methods, we chose three characteristic airflow rates at characteristic pressure differences. The first one is at 50 Pascal pressure difference, and the other airflow rates are evaluated at 4 and 10 Pascal pressure difference for subsequent analysis. The acoustic setup looked like this. So we had small microphones in each of these chambers and a speaker in one of the chamber. The actual measurements had been conducted with a plate sealed both chambers on top. So this is just for illustration purposes here. We used as an excitation signal white noise, a broadband white noise signal, and we did an analysis of the frequency range between 0 and 40 kilohertz, which goes up until the ultrasonic frequency range as well. The parameter we evaluated here is the so-called coherence, which is a description of the fraction of an output signal from an input signal at a specific frequency, and it measures the linear dependency between two discrete time signals we have here. We have a time signal in one chamber in the sending room and in the receiving room at the other side. This coherence is defined as the squared magnitude of the cross-spectral density between these signals divided by the product of their autospectral densities. This factor has the advantage that it's always between 0 and 1, whereas 1 means that both signals have at this specific frequency a total dependency, and 0 means that they're totally independent from each other. So here I'll show you the same measurements I showed you earlier at the fan pressurization methods measurements. With the same configuration, you see the frequency from 0 to 40 kilohertz on the x-axis, and the coherence from 0 to 1 on the y-axis. All these colored lines are the same measurements as I showed you earlier for the fan pressurization methods. You still see that the blue line with the largest slit has the highest correlation between both signals for this whole frequency range. Additionally, we added here a measurement where we measure the acoustic signals for a tight wall as well, without any deliberate opening in it. Because in contrast to the airflow measurements, we have still sound transmission through the construction, even though there's no airflow in it. So we wanted to evaluate the influence of the actual leak in relationship to the sound transmission through the construction. For a first guess, or like an easy evaluation of this, to get an easy value of this, out of this evaluation, we just took the mean value over the whole frequency range for all these slit configurations, and we see here that there's in the mean value we see a clear difference between all of these investigated wall structures. In order to reduce the impact of the tight wall and the sound transmission through the structure itself, we took for the subsequent analysis just the difference between a measurement with an opening and the same wall construction without any opening. So in order to see if this is a reliable, or if we can predict the size of a leak or the airflow of a leak, we compared this value with the measured airflow rates we measured earlier. So we see here on the x-axis this mean coherence value difference, and on the y-axis the airflow rate at 50 Pascal in this case. And the dots are all the measurements we had for these 43 different configurations, and the line is just the least square fit between them. Here we can see that in the mean we have an increasing airflow rate with an increasing coherence difference, even though we have some outliers on the top and on the bottom. So we could at least estimate the order of magnitude of the size of the leak with the coherence difference with these acoustic measurements. We did this for the same analysis for the airflow at 10 Pascal and the airflow at 4 Pascal as well. Here we only changed the airflow rate, but not the coherence is not changing. And we see that the absolute difference between this fitted line and the airflow rates is decreasing with decreasing airflow, with decreasing pressure, evaluated pressure differences. So to conclude this, we did airflow and acoustic measurements within the same laboratory environment and within the same boundary conditions. We investigated 43 different configurations here, and we saw that a distinction between different leak sizes was possible within the acoustic methods, and it was possible to get at least an order of magnitude of the leak size. But up until now, we only took the mean value over the whole frequency range with an identification of possible dominant frequency bands within this analysis and a weighting around. Then we hope that we might increase the prediction accuracy in future analysis. Furthermore, more complex and more different leaks might be investigated here, and the applicability in real buildings. And we'd like to investigate a potential for localization of leaks using other acoustic methods. So I thank you for your attention, and I'm now more than happy to answer questions.